There we go. Okay. So first, let's just take a minute to review what we learned last week. So I'm going to tell you what the mechanism is, SN1, SN2, SN1, and then elimination. And you're going to take a second and give me the products of these reactions. All right, so SN2, the S means we have a substitution. Somebody's swapping out my leaving group for my nucleophile. All right, and because it's an SN2, this is the type where I have this inversion in my stereochemistry. Okay, so when I draw my products, I'm going to draw my dashes. I'm going to flip, so my dash becomes a wedge. Oh, that's not going to work. Rather, my wedge becomes a dash. So I got these same 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. Okay. And then on that third to last carbon, instead of drawing a wedge, I'm going to draw a dash. And which atom in my nucleophile am I attaching to that carbon, the hydrogen or the sulfur? The sulfur. Okay. So the 2 means that there's an inversion. SN1 is also substitution. But remember, for this one, we got to draw both products. Right? So the 2 is the inversion where you only have one product. The 1 is where we have to draw both products. Seems like it's backwards, but that's not what those numbers mean. It's a little bit more in depth than what we're going for here. You're just going to trust me that it's called SN1 and SN2. For the 2, there's an inversion, and for the 1, you have to draw both of your products, right? So I'm going to draw 1 where I don't change any dashes and wedges. So you're going to stay a wedge. And then my leaving group on my dash is going to be replaced with what? Also SH, right? So remember, we had 2 different types of nucleophiles. These ones were negatively charged. You just attach that negative charge, becomes a new bond. But for our neutral nucleophiles, remember, they lose a hydrogen. All right, and then I have to, again, I got to draw both, so I'm going to draw 1 more. That didn't work. But this time, I'm going to replace my wedged bond with a dash. So that goes there, and my dash bond with a wedge. So those are my 2 substitution products that I get for my SN1 reaction. All right, and then elimination means that I'm creating what new functional group? An alkene. All right, so I'm going to draw my square. But again, now I'm going to put in a double bond between this carbon and one of its neighbors. In this case, it actually wouldn't matter which one I picked because I would get the same product. So this is my alkene. Right, so we have 3 different possibilities here. SN2, where we have the inversion in our substitution stereochemistry. SN1, where we have to draw both products. And then finally, an elimination reaction, which leads to our alkene. Okay, I guess if we want to be like really thorough with this set of examples, let's go ahead and put a methyl group on here. So then we can note that our alkene forms, we get the more substituted alkene. Remember, we had this logic behind which carbon is going to be chosen to do our elimination reaction. We're always going to pick the one that gives us the more substituted alkene. All right, cool. So we've kind of been laying a bunch of groundwork here in order to sort of determine which one of these 2 reactions is going to be the actual like major product of your reaction if we just are given these 2 substrates right here, right? So now what we're going to learn is based on what type of alkyl halide we have and what type of nucleophile, we can determine which type of reaction it's going to undergo, okay? So one of the things that we're going to be given on our constants page, there's a copy of this up on Canvas. This is what you'll be given on your exam here. These are these nucleophile / bases thrown into these 3 categories. Okay? So you don't have to memorize this table or anything like that. You just have to know how to use it. All right? So let's just go through and look at what we have here. This first category are things that are strong bases, but then bad nucleophiles, weak nucleophiles. Our next category is things that are both strong bases and strong nucleophiles. Our next category is things that are crappy bases, but are good at being nucleophiles. All right, and then the last category is of things that are both weak bases and weak nucleophiles. Okay, so let's just remind ourselves real quick. We called them nucleophiles when they were involved in which of our two reaction types, substitution or elimination? Substitution. So our nucleophiles prefer substitution reactions. We called them bases when they were involved in elimination reactions. All right, so again, you're going to be given this chart on an exam, this table rather. What you need to be able to do with this table is to create this chart that we're going to make below, okay? So that's going to be the first thing you're going to do on your exam is you're going to be given a chart, this table right here, and you're going to need to build this chart that we're going to build right now, okay? So what we're going to do is we're going to group our alkyl halides into one of three categories: primary alkyl halides, secondary alkyl halides, and tertiary alkyl halides. Okay, so let's just do an example of each real quick. The halogen itself can only ever be bound to one carbon, right? Halogens can only have that one bond. So in order to figure out whether we have a primary alkyl halide, a secondary alkyl halide, or a tertiary alkyl halide, we're really looking at the carbon at the base and determining whether it's a primary, secondary, or tertiary carbon. Okay? So this carbon right here has one carbon neighbor. This would be an example of a primary alkyl halide. Okay, again, that chlorine, that halogen, it can only have one bond, so I'm not looking at how many carbons the chlorine is bound to. I'm looking at the base and counting how many carbon neighbors that carbon has. So this has 2. This would be a secondary alkyl halide. All right, and then lastly, this one here, I look at the carbon at the base. It has 1, 2, 3 neighbors. This is a tertiary alkyl halide. All right, there's one more sort of position that we want to note here that kind of is a little bit of an exception, and that is when you have a benzene ring. All right, and the carbon right next door. Oops, let me finish off my benzene ring. Has that halogen. This is what's called a benzylic position. Okay. Carbon next to benzene ring. All right, so it'd be very tempting to look at this compound here and say that it's a secondary alkyl halide but because it's right next to that benzene ring, it gets its own special name. Okay? So these are our three types of alkyl halides that we need to be able to spot: primary, secondary, and tertiary, but also this benzylic position, which is again located right next door to a benzene ring. Okay? And we're going to throw that benzylic position into this tertiary bin. It turns out that they behave more like tertiary alkyl halides. So tertiary and benzylic are going to go into the same category. All right, so we're making this chart here. For each of these categories of alkyl halide, we're going to be able to tell, based on what category that other thing falls into, what type of reaction we have. Okay, so this is our chart that we're going to fill in. This is what you need to be able to fill in from memory here. You'll be given this top part. You need to be able to fill in this part here. Okay? Before we go on, let's just go back to our same examples that we started out with. Everybody take a second and figure out whether we have primary, secondary, or tertiary alkyl halides here. For this first one, what do we think? Primary, secondary, or tertiary? Secondary, right? I'm going to look at the carbon at the base of my halogen. It has these two neighbors. That thus is a secondary alkyl halide. What about this one? So be careful, it is a six-membered ring, but it's not a benzene ring, right? So that's not going to be that benzylic one. I'm just going to look at the base, and I'm going to count 1, 2, 3 carbon neighbors. All right, so this is a tertiary alkyl halide here. And then what about this one? This is just secondary, right? So again, I'm going to look at this carbon and count. It has 1, 2 neighbors. I'm not going to count this one, right? It's too far away. It's not attached to that carbon. So it's how many neighbors this carbon right here has, which is just 2. So this is a secondary. All right, so that was step 1. We got to figure out what category our halogen falls into, and then look up which category the other thing falls into. Okay? So in this case, our options on our previous page were doesn't matter, SH minus, SH2, and then finally, what was it? Oh. All right, so let's take a second and see if we can't find these on our chart here. I see a bunch of R's. What do the R's mean? Stand-ins for carbons and hydrogens specifically, right? So R, O minus, means that it could be CH3O minus, or even longer than that. Any of those would be this ROH, or RO minus, right? The R is just this variable, stands for an alkyl group. Of any size. right, notice that my sulfurs, we got two sulfur compounds here, both of which fall into this category here. I guess it's actually these two. All right, of a weak base and a strong nucleophile. All right, whereas this one here is that some amount of carbons and an oxygen with a negative charge. All right, so let's fill in this chart here. So, first of all, the two easiest categories are the strong base weak nucleophile and weak base strong nucleophile, okay? And that's because, again, bases like to do elimination reactions. Nucleophiles like to do substitution reactions. So if something is considered to be a bad base, or I'm sorry, a bad nucleophile, but a strong base, then it's going to prefer elimination reactions across the board. Doesn't matter what category it's in, it's going to want to do an elimination reaction because it's a strong base but a bad nucleophile. Again, bases will promote elimination reactions, nucleophiles will promote substitution reactions. All right, so then if we have the other sort of the flip side, something that's a bad base but a good nucleophile, what type of reaction do we think they're going to prefer? Substitution reactions, right? This is where it gets a little tricky because we have two different types of substitution reactions. Primary and secondary undergo SN1. But tertiary reactions and benzylic undergo, I'm sorry, did I just mix that up? Primary and secondary undergo SN2, but tertiary and benzylic undergo SN1 reactions. Okay, so then the other ones, the sort of less intuitive categories are, what do you do when it's both a strong base and a strong nucleophile? Now that competition between the two is really important, right? Because this thing, for example, a hydroxide ion, it's both a really good nucleophile, but it's also a really good base. So that competition between these two is going to be really important. For primary alkyl halides, it turns out that your substitution product is the major product. But for the bigger ones, for secondary and tertiary, it's instead elimination. All right, and just to sort of explain why that is, so again, let's just look at this thing here. Everybody take a second and tell me what type of alkyl halide this is, primary, secondary, or tertiary. This will be secondary. All right, and let's just compare that to one that's very similar. I'm going to draw it very similarly. But now this one's just a primary alkyl halide. All right, if we react these with a strong nucleophile that's also a strong base, something like this hydroxide ion, in the case of a secondary, right? Let's make sure that we can use our chart. In the case of a secondary alkyl halide, what's the major product? The elimination product. And in case of a primary, what's the major product? substitution, right? We're in this category here. So everybody take a second and draw me the two products of these two reactions, very similar. All right, so in the case of secondary, we have an elimination reaction. And remember, we're going to get that more highly substituted alkene. So here's my elimination product. And in the primary, I'm going to instead have my substitution product. All right, so why is it that for a primary, it's the substitution product, but for a secondary, it's the elimination product? Okay, this is what we would call, we've actually heard this term before. The reason is what's called steric hindrance. Does anybody remember what steric hindrance means? We talked about this with our cyclohexanes and why those big bulky groups like to be in the equatorial position as opposed to the axial position. Space, exactly, right? So it's just an amount, it has to do with how crowded this carbon is relative to this carbon, right? For something to play the role of a nucleophile, it has to be able to attack that carbon. And secondary carbons are just less accessible than primary carbons. These are more accessible. All right, secondary carbons are simply more crowded. Primary, you got more space. All right, so there's this competition between these two reactions, substitution and elimination. If you have a secondary, or of course a tertiary carbon is going to be even worse, right? Even more crowded. But primary carbons are nice and accessible. Those will prefer substitution reactions. But secondary and tertiary carbons, they're just too crowded. They're going to prefer elimination reactions.
For the elimination reaction, why did you put the double bond where it is like compound?
Because, so remember, it's going to have to involve this carbon here. So I had two options. Could have either been this one or this one. And remember, it's always going to be the more substituted alkene. Right? This alkene over here is mono-substituted. I'm going to look at this carbon. It's got no neighbors. I'm going to look at this carbon. It's got one neighbor. All right, whereas this alkene is di-substituted. This carbon has one neighbor, this is another one, so this is a di-substituted alkene. The more substituted alkene is the one that's going to be your major product in an elimination reaction. All right, last thing we got to do to fill out this chart, and then we'll just practice the crap out of this, is for our weak bases and weak nucleophiles. So these are things that are pretty terrible at both. Turns out that these do not react with primary or secondary alkyl halides, only with tertiary alkyl halides. All right, but there's this competition where you're going to get a 50-50 mixture of your SN1 product and your elimination product. So weak bases and weak nucleophiles, things that are bad at both, they don't react with primary or secondary alkyl halides, but they will react with tertiary and benzylic alkyl halides. And there will be both an appreciable amount of your substitution and your elimination product.
Will we go over on how to decide between the weak base and weak base as to which 50-50, or do we draw?
No, you're going to draw both. It's always going to, it's considered to be an appreciable amount of both, which means that we need to include both of those products, both substitution and elimination. All right, so let's just practice using our chart here, okay? I'm going to put down an alkyl halide and then a base or a nucleophile, right, our reagent, and you're going to tell me what the major product is. All right, so let's just do one of them together here. Okay. So, first of all, let's look at our halogen here. And everybody take a second and determine whether we have a primary, a secondary, or a tertiary halogen. Yeah. All right, so this would be a primary halogen. So now we need to find this thing on our chart, okay? Everybody take a second and see if this is kind of a difficult one to spot here because it's all written in their condensed formulas here. Yep, weak base, strong nucleophile. So specifically this thing right here, COO minus. So it would be an SN2 reaction here, right? Because we got primary, we got a weak. So this would be an SN2 reaction. All right, so to be clear, we can sort of just make our notes here. This is this R COO minus. Right? Here's the C, here's the O, here's the O with the minus sign. All right, and exactly, since our chart tells us this is going to be an SN2 reaction. So everybody take a second and draw me my SN2 product. All right, and pay special attention to which atom you're sticking on to your electrophilic carbon. Right, remember this, we call it a leaving group. And this carbon at the base of that leaving group we called our electrophile. This over here we called a nucleophile. And which atom in my nucleophile is going to be bound to my electrophile? The oxygen, right? It's going to be one of those heteroatoms and the one with the negative charge. So there's my 3 carbons from my electrophile. Here's my electrophilic carbon, rather. Attach it to an oxygen. Now it's got that carbonyl. Boom. All right, so to be clear, this chunk here, these 1, 2, 3 carbons, they are from my electrophile, and these 1, 2 carbons, that was in my nucleophile chunk. All right.
Because SN2, we usually call it an inversion. Since this doesn't have any dashes or wedges, we're just going to draw it out.
You just draw it as a straight line, yep. If there's no specified stereochemistry, no specified dashes or wedges, you can just leave it as the regular line. There's nothing to flip. All right, so everybody take a second to copy this problem down, and then we'll flip it back to our chart.
So for the exam, that chart we just made, it's gonna be filled in, like, we're gonna know which stuff, like, if it's gonna be elimination or.
No, that's what you have to do. You're going to be given the bones of the chart. You're going to fill in this portion here. All right, so, oops, sorry, I don't know if this got erased or what, but there should be a minus sign on this nitrogen. All right, so here's my substrate and my reagent. So everybody take a second and using this chart here, see if you can't figure out what category of reaction we should have draw our product as. What's the major product of this reaction? All right, what type of alkyl halide do we have? That would be a tertiary, so it's going to be for this row here. And then what about our reagent? What was that? This thing right here, right? So that's a strong base and a strong nucleophile. The two together will prefer an elimination reaction, right? So here's my in this case, strong base, strong nucleophile. I had a tertiary, so that's how I know this is going to be an elimination reaction. All right, so everybody take a second and draw me my product, because now we've just figured out that we have an elimination reaction. All right, and PACE special, I want everybody to double check how many carbons they have on the left and how many carbons they have on the right. Okay, so my elimination product is going to be an alkene, right? I got to draw that double bond. It's either going to be between this carbon and one of these three. In this case, they're all identical, so it wouldn't matter which one we chose. Okay. I'm going to draw them all nice and spaced out like you would normally see. All right, but we have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. This one in the middle is what used to have that halogen on it. Okay, we can kind of think about it like I'm taking this pair of electrons here from this double bond, or from this bond. Right, it used to be here, now I'm moving it down to form a bond with one of its neighbors. Right, but we don't really draw, it would be kind of weird looking to draw something like this, so all I did was space them out. Get rid of all of these markings. All right, let's do another one. Actually, we already did that one, didn't we? All right, so going back to our chart, so everybody copy down our substrate and our reagent here. Go back to our chart, get rid of all these markings. All right, and what category was that alkyl halide? The alkyl halide, the thing with the halogen on it, primary, secondary, or tertiary? Secondary. And then the other thing, our reagent was weak base, strong nucleophile, right? N3 minus. So that means we're going to be drawing the SN2 product. So I'm going to flip my stereochemistry. My wedge is going to become a dash. Okay, and 3. All right, and we can just draw this out, the whole structure for our homework here. So you can abbreviate it like that is fine, but you'll have to draw out the full Lewis structure here. And so this is this weird kind of deal here. Got all those 3 in a line, 3 nitrogens in a line, everything double bonded to that middle nitrogen. All right, and then lastly, just real quick before we go, what if I gave you something like this? All right, just to sort of go through the process here, what category does this alkyl halide fall into? This is this weird one. It looks like it's primary because it's of that carbon there, but remember, it's right next door to that benzene ring. So this would be that special case, that benzylic position, right? And so in this case, our weak base, weak nucleophile water and our benzylic carbon here, this would be this mixture of SN1 and elimination reactions. Okay. All right, but this is kind of a special case here. Just to kind of go, wow. So my substitution product is pretty straightforward. Everybody take a second and try to draw me the elimination product. Say SN1. Okay, so if I go to draw my elimination product, I would get something, it's got to be between this carbon here, and it's only got this one neighbor. What's the problem with this elimination product right here? What's the problem with this structure? Yeah, what's wrong with this carbon right here? It's got way too many bonds going on, right? This carbon has 5 bonds. This cannot exist, right? So there would not be any elimination product just because there's not a possible double bond to draw, right? Really, it's because this carbon right here, there's no hydrogen, so you can't have an elimination product. All right, so just be careful, make sure you're not drawing anything illegal. Elimination is not possible. All right, so this is the last little bit of new information that we have for this chapter, but we're not going to start off on chapter 7 next time. We're going to review the crap out of this, all right, because this is kind of some tough stuff here. We need to practice drawing these structures. It's hard enough, never mind having to decide between what mechanism it is. So anyways, we're going to just spend next class just reviewing and using this chart again, drawing products for these reactions.